Hello! Today we're going to talk about Ka and how that relates to acid strength. It's the quantification of what we talked about in the previous video, acids and bases, and weak acids and bases. So, we have this equation. So I'm using hydrofluoric acid as my kind of model weak acid. And so hydrofluoric acid with water will form hydronium and then the fluoride anion. Alright, this is a great example of a weak acid. Now, quite commonly we want to know what the pH is here of a weak acid. And so, unlike strong acids and strong bases, we need to do equilibrium calculations to solve for the concentration of H3O+, which we could then use to find the pH. So it gets a little trickier with weak acids than it does with strong acids. So, like all equilibria, we can write an expression for K. Here's the expression for K in terms of concentrations. It's aqueous. It makes sense to use concentrations. And now, this is a special equation. The equilibrium constant for this, we call it Ka instead of Kc, to show that it's specific for this one type of equation. If Ka, then acid dissociation. This gets confused with a bunch of other equations later. Just remember, Ka is this one, your acid splitting apart to make H3O+. Now, bigger Ka, more products, which means it's a stronger acid because it makes more H3O+. Hydrofluoric acid, here's its Ka, 7.1 times 10 to the negative fourth. HCl is a strong acid, so its Ka is crazy big. That's almost, it's tricky to measure that because it's so big. So we don't use this type of discussion when we're talking about HCl because it just doesn't make sense. For HF, it does make sense to do this equilibrium kind of discussion. So, generically, we write it this way. Ha plus water makes H3O plus and A minus. And so A refers to whatever else is attached to this hydrogen. They all function the same way, right? You got the hydrogen, you got something else, and it's equilibrium with the hydrogen pops off, makes H3O plus, and then whatever the heck is left. So we have conjugate acid-base pairs here, right? HA is the acid. We use A for acid. Makes sense. It reacts with the base. And then the acid, HA, has its conjugate base, which is just whatever's left. And then water is functioning as the base here. The H3O plus is the conjugate acid to that base. All right. So then, again, we don't so much follow the conjugate bit about the water, but, the acid makes its conjugate base. And this becomes really important because if you have a mixture of a weak acid and its conjugate base, that's called a buffer. And all of biochemistry and biological reactions is all done in buffer solutions. Your body is one big buffer. We talk about buffers a lot in the next chapter, right? And a buffer is just an acid and its conjugate base mixed together in somewhat equal proportions. So, this part's important. We can talk about Ka, that was on the last slide, but here it is generically, right? A minus is on the top, HA is on the bottom. We use this a bunch when we talk about acids and, theory and how to do this because it's generic, right? So we just talk about HA. So that's what it means. You can talk about pKa by taking the negative log of Ka. I mentioned that in a previous video. And then you can go the other way, right? 10 to the negative pKa gives you Ka. So here's a table of various values for weak acids. It's at 25 Celsius. Pretty much everything we do with pH is designed for 25 Celsius. And so just here's the value. You have a wide spread of values depending on the acid. There's some relationship between molecular structure and Ka that we don't really get into in this course, although it's important, and you get into that in organic chemistry. So it's just a table. You can look these up, right? They're not surprises. Now, an important note is that different sources, different books, different people, sometimes me, the same person, talks about these differently, right? You can either add or remove water from both sides of this equilibrium, and they're pretty much interchangeable, right? The bottom one is the one that's more technically correct because you don't have free protons floating around in solution. They usually jam onto a water molecule. But hey, it's easier to say the top one, right? So the top one's less ink, easier to talk about. The bottom one's more correct. When I first started teaching, I used the top one. And then I realized I should do this right. So then I started using the bottom one. So they are roughly interchangeable. Okay, so the big type of calculations we do here is you have some acid, you have some concentration, we're trying to find the pH. We do that a lot. You can go the other way as well, right? And just This is just a calculation. So let's do this, right? This is really important. We do this a lot. Let's do it right the first time. So acetic acid, it has some Ka value. And so say you put a mole of acetic acid into 1 liter of solution. Surprise, that makes 1 molar solution, moles over liter, 1 divided by 1. Okay. What's the pH of this? So, since it's a weak acid, we need to use equilibrium calculations, which is most easily expressed through an icebox. And so here's the equation again. And whenever you talk, actually, I shouldn't say here's the equation again, because we haven't given it to you. That's something that's new here, is we say acetic acid, we say Ka, then you need to know that that means this, right? A Ka equation is Ha, so here's the A minus over here, here's the H plus, and then together they're Ha, and then here's the A minus by itself over here, and here's where the H plus goes, right? So this is that equation. It's something you need to know. All right, so I'm going to throw the initial concentrations in. Another thing we do is we say, okay, we have this solution, what's the pH? And the way to do the math that's easiest is you just imagine, hey, say I started with only acetic acid, not dissociated yet, so that's your initial, and then you see where it goes with equilibrium. You don't include the water in this because it's not in the equilibrium constant because it's a liquid. Another thing you don't worry about is the autoionization of water. So this is true, right? The water is dissociating by itself into H3O plus and OH minus. That's a source of H3O plus. So if you wanted to be true about it, you could say that this is 1 times 10 to the negative 7th right here. Like you could throw this number into here. And you could do your whole math with it. It would complicate your math a little bit, but overall it'd be technically correct. And you would see that starting with 1 times 10 to the negative 7th doesn't make a lick of difference. So we ignore it to make our life easier. So we generally don't consider this, and then we just start with 0 for the H3O plus. Now this is moving to the right because it's going to fill in these zeros on the right side, so your equilibrium shifts right. That's straightforward. You add the top 2 lines, get the bottom line. Great. Now, like normal for iceboxes, we take the form of the Ka expression, which is the products over the reactants to their stoichiometric coefficients. The nice thing about this is that as we define the Ka equation, it's always 1. There's no exponents in here, so that's nice. And then this is equal to the Ka. Okay. And then you have x squared divided by 1 minus x, just the way that the icebox works out. And this is really, you'll see this type of thing a lot, right? You're just changing around Ka values, you're changing around concentrations, but overall the structure of this and how it looks is going to be the same. All right, now we just got to solve for x. You can do this a couple different ways. So one, this is a quadratic, right? A second order polynomial. You can rearrange this for a, b, and c. It's a lot easier to do for this type of equation than it has been before. And then you plug it into the quadratic equation either by hand or in some quadratic solver on your calculator or whatever, and then you get x. You get the roots of that. That's the precise way to do it, and that gives you the right answer all the time. But it's kind of a pain, right? So another thing you can do is often assume that x is small and neglect it. So 1 minus x, you say, that's pretty close to 1. We talk about that in the next video. You can also do something called the method of successive approximations. You can do, and we'll talk about that in the next video as well. There's just other ways to solve for x. We're going to do it right the first time. So here's the quadratic. You do all that work. You get the roots of your quadratic, or this. And then you can't really have negative concentrations. So you cut that one out. And then now we have x. I generally assume, like coming in and out of the quadratic, if I've got 3 sig figs before, I'm going to have 3 sig figs after. It's far and away easier than trying to follow sig figs through the quadratic formula. So if you do this, just give me the same sig figs as you had before, especially if you come out of some quadratic solver or something like that. Okay, so now we need to get back to pH. What is pH? So the short way to do this is just to remember from your icebox on the previous slide that, hey, the concentration of H3O plus is just equal to x. Hey, look, we found x. So then you just take that and you take the negative log of x, and then you find pH. That's the short way to do it. Again, we're doing it the first time. Let's do it right. So I'm going to use another icebox to be thorough about it, but this one I'm not trying to find x. I know what the initial is, that's the same, but now I know what x is, and we're going to subtract x from the left side, add it to the right side, and then evaluate these. Add the top two lines together at equilibrium, here's what we got. And so if you ever have a problem that wants to know concentrations of everything, you can do it this way. Always a good idea to double check, did you solve for x correctly? Throw all these values that you found back into the Ka expression, and you should get whatever the Ka is. Good idea to double check that. Now we can solve for pH. Again, pH is the concentration of H3O+, so this number is what we care about. And then you take the negative log of that and you get pH. Again, we could have done this without doing this kind of second icebox idea. I was just going to be thorough the first time around. Once you find X, when you're dealing with Ka, that is H3O+. Another fun thing you can do is if you measure pH experimentally, you can find what the concentration of H3O+ is, and then plug that back into here, and then you know what X is in your icebox. So we do that in the lab. And we can do that in lecture as well. It's just kind of a backwards way to do this whole thing. And we'll have some examples of that in class. But that's all I have for now, how to do a Ka calculation. Again, this is really important. We do it over and over again and build on it. So make sure you take the time now to understand how it works, and you should be set. All right, thanks for watching.